Our next lesson in the module on graphs will be about graph connectivity. So this section will be devoted to the question that when posed in relation to graphs could seem trivial. The question is, given two vertices S and T of a graph, is there a path from S to T? If S is equal to T, then this question would be interpreted as asking whether there is a circuit of positive length starting at S. And for the graphs that we've seen so far, the question could be answered briefly after examining them. There are two situations under which such a question is non-trivial. One is where the graph is very large and examination of the graph could take a considerable amount of time. The second interesting situation would be when we want to pose this question to a machine. If only the information on the edges between the vertices is a part of the data structure for the graph, then how can you put that information together to determine whether two vertices could be connected by a path? So we'll address some terminology really quick. Let V and W be vertices of a directed graph. Vertex V is connected to vertex W if there is a path from V to W. And remember, we learned what a path is in our previous lecture, so it doesn't have to just be a direct connection in the form of an edge. You may have to travel through multiple edges and multiple vertices to get there, but if there is a path. Then two vertices will be strongly connected if they are connected in both directions to one another. A graph is connected if for each pair of distinct vertices, V and W, V is connected to W or W is connected to V. So we have the idea of two vertices being connected. We say that the whole graph is connected if this is true for all of the vertices. If for any two vertices, V and W, either V is connected to W or W is connected to V. And the notion of strongly connected is if there's two-way connection between V and W. So we can also extend that to the idea of a graph. A graph will be said to be strongly connected if every pair of its vertices is strongly connected. Now, of course, for an undirected graph in which edges can be used in either direction, then the notions of strongly connected and connected are the same. So you'll see a theorem here, which is the maximal path theorem. If a graph has n vertices and vertex U is connected to vertex W, then there exists a path from U to W of length no more than n. So what are we assuming here in this theorem? We're first assuming that the graph has n vertices. We're also assuming that vertex U is connected to vertex W. So we know that there's a path. The theorem just tells us that the path cannot be longer than the number of vertices in the graph. And there's a proof here. So we prove this indirectly, which means we're aiming for a contradiction. We start by assuming, well, what if U was connected to W, but the shortest path was bigger than M? The shortest path had length n, where M is bigger than n. Then a vertex list for the path would have m plus 1 vertices and could be represented, as you see here, something like this, V0, V1, Vm. So this is the vertex list for this theoretical path from U to W. And then we notice that since there are only n vertices in the graph, and m vertices are listed in the path after V0, then we can apply the pigeonhole principle to find that there must be some duplication in the list. And that duplication would represent a circuit in the path. So that means we should be able to remove that circuit to find a path of smaller length, but we assumed that this path was the minimum length. So we've come to the point where we're saying the path of minimum length can be made shorter, which is a contradiction to the idea of minimality. So the basic questions that we're hoping to address would be, given a graph and two vertices, is there a path from the first vertex to the second? We want to be able to answer that question. And if we can answer yes to the question, then we'd like to be able to find the path. So we're hoping to build some tools that will help us to answer these questions. So the first thing, we know an adjacency matrix. In an adjacency matrix, two vertices, if they have an edge connecting them, then there'll be a 1 in the corresponding entry of the matrix, otherwise a 0. So suppose that the information about edges in some graph, capital G, is stored in an adjacency matrix. The relation R that G defines is V relates W. Remember when we see that R is a relation and we have VRW, we're saying V relates W if there is an edge connecting V to W. Now we can compose the relation R with itself, and that's going to be defined by R squared, and we'll write V R squared W. And what do we mean by composing the relation with itself? So we'll write V R squared W if there exists a vertex Y such that V is related to Y and Y is related to W. So some intermediary path or intermediary vertex. So that is, V is connected to W by a path of length 2. We could prove by induction that the relation R to the power K is defined by V R to the power KW if and only if there's a path of length K from V to W. And in fact, we are going to do that in just a little while. Okay, so the main advantage of the adjacency matrix method is that the transitive closure matrix, and there's more information about what that matrix is in the paragraph above. The transitive closure matrix can answer all questions about the existence of paths between any vertices. So using adjacency matrices, we can answer questions about the existence of the path. And a directed graph will be strongly connected if its transitive closure matrix has no zeros. So let's try to make sense of that. We said that the directed graph would be called strongly connected if there was two-way communication between each of the vertices, or if there's a path connecting vertex V to W and a path connecting W to V, then we say it's strongly connected. And so then it would make sense that the adjacency matrix would have no zeros because this will be true for all of the vertices. But a disadvantage of the adjacency matrix method is that the transitive closure matrix only tells us about the existence of a path, but it doesn't help us to find what the path is. So our first question above, you recall, was, is there a path? And using adjacency matrices, we can answer that question, but we can't answer the next question, which is, okay, now find the path. So the next algorithm, which is called breadth first search, is going to help us to find the path. So we're just going to describe the breadth first search algorithm, and then it will be included here in the lecture note. But this description, I think, should give you a pretty good idea. So this is kind of a long example, but we'll just go through it. So let's say there's a football team at MSU that has a bad year, 2 wins and 9 losses. So 30 days after the end of the football season, the university trustees are meeting to decide whether or not to fire the head coach. But on the day of the meeting, the coach issues a press release with the following results. So the press release says that ESU was the national championship that year, and the coach has found this chain. His team, MSU, defeated local A&M. Then local A&M defeated City College. City College defeated Corn State University, and 25 more results later, some other school defeated Enormous State University, who went on to win the national championship. So the coach releases this as a press release, and the trustees are so impressed that they decide to rehire the coach and with a raise. So how would the coach find such a list? He would use a breadth first search, because essentially what he's found is a path from his school to the championship through teams that they beat. Okay, so in reality, such lists exist occasionally and have appeared in newspapers from time to time. Of course, they don't really prove anything, since each team that defeated MSU in our example could produce a similar, shorter claim of results, right? If you were the 7th step down the list, then you're 7 steps closer to claiming that you could have competed with the champion. So it's not necessarily logical, but how did the coach produce such a list? He needed to start with the fact that his team won at least one game. And since the champion lost at least one game, then there would be some hope of producing this chain. The problem of finding this list would be equivalent to finding a path in the tournament graph for last year's football season that initiated at MSU and ended at ESU. So such a graph, we know, is far from complete. Let's remind ourselves that in order for a graph to be complete, there would have to be edges between all of the vertices. So since the graph is clearly not complete because not all of the teams compete with each other, and it's likely to be represented using an edge list as opposed to adjacency matrices, which again we talked about in the previous lecture. So to make the coach's problem interesting, let's imagine that only the winner of any game, only the winner remembers the result of the game. Then the coach's problem has taken the flavor of a maze. To reach ESU, he must communicate with the various teams along the path, and one way that the coach could have discovered his list is by sending the following messages to the coaches. So this is the coach's letter. He says, "Dear football coach, please follow these directions exactly." So this, you can think about forming the algorithm of talking to the computer. Try to translate this in your head. So the coach says, "If you are the coach at ESU, contact the coach at MSU now and tell him who sent you this message." So that's like telling the computer, if it found the path, then it should spit out the information to you. If you're not the coach at ESU, and this is the first message of this type that you've received, then remember from whom you received this message. Forward a copy of this message signed by you to each of the coaches whose teams you defeated during the past year. Ignore this message if you've received one like it already. Signed, Coach of MSU. So, if you're not the terminal vertex that we're looking for, if you're not ESU, then what I want you to do is just forward this message to all of the coaches of the teams that you beat. So each coach receiving this is going to forward this along to all of the teams that they beat. So from the conditions of this message, it should be clear that if everyone cooperates and if coaches participate within, say, 1 day of receiving the message, then the following. If a path of length n exists from MSU to ESU, which is what we're looking for, then the coach will know about it in n days. So if the path is length n, then it will take n days. And you'll remember that there were like 28 stops on the path, if we went back to the list that he presented at the press conference, and it said it took him 30 days to find this list. So we're assuming that the coaches are all doing this within 1 day of being asked to do this. So if the path exists, then we will know about it in n days. The second thing we could observe is that by making a series of phone calls, the coach could construct the path that he wants by first calling the coach who defeated ESU, the person who sent ESU's coach the message, and then this coach would know who had sent him the letter, and so on. So the ESU coach can tell you who sent him the message, then that coach can tell you who sent them the message, and going backwards that way. Therefore, the vertex list of the desired path is constructed in reverse order. The next thing to observe is that if a total of M football games were played, no more than M messages will be sent out. Also, because we're assuming that the coaches are following up on this within one day, if a day passes without any message being sent, then no path exists. If a day goes by and no message is sent, then we assume that that coach had already received the message, whoever the last person to get it was, and there are no more avenues to follow. So then we conclude that no path exists. This method could be extended to construct a list of all teams that a given team can be connected to. Simply imagine a series of letters like the one above sent by each football coach and targeted at every other coach. The general problem of finding a path between two vertices in the graph, if one exists, can be solved exactly as we solved the football coach problem. And the following algorithm is called breadth first search. So just like the process that we just described above, this is what this code is doing. And I'm not going to go through it in detail, but if you are interested, do take some time to read through it and try to connect it back to the ideas that we just talked about. The key thing here is that the vertex list will be constructed in reverse order and in the method that we described. Okay, so a couple quick notes on the algorithm. The algorithm will produce one path from vertex I to vertex j if one exists, and the path will be as short as possible. So this is what we want from an algorithm. We want it to give us the results, and ideally we want it to give us the results efficiently. If more than one path of this length exists, then the one that is produced depends on the order of which the edges are examined. That makes sense. So the condition that D sub r, and again you can go back and read the algorithm, but if we turn up empty, then that would be analogous to the condition that no mail is sent in a given stage of the process, so we conclude that there is no path. And also this algorithm can easily be revised to find paths to all vertices that can be reached from vertex I. So in particular, we were looking for a specific path to a specific vertice, a vertex, but you could easily edit this for your purposes. So a simple example, if we look at the graph here on our screen, the existence of a path from vertex 2 to vertex 3 is not difficult to determine. After a few seconds, you should be able to find two paths of length 4. So let's examine this and see what we find. So I'm starting here at vertex 2, and my aim is to end up at vertex 3. And because these are directed edges, I can see that I'm not allowed to go this way or this way coming out of vertex 2, because those are coming in. So my first choice is just to go this way to vertex 1. Now that I'm at vertex 1, again, I can see I'm not allowed to go this way or this way. So I can either choose left or right. Let's say we take a left turn and we go down to 4. Then from 4, I'm not allowed to make this choice because that's coming into 4. So I can go from 4 to 6. And then at 6, I can't take this path. I could take the middle path, but that's taking me back to vertex 1. My end goal is to get to vertex 3, so I'm going to continue on to vertex 3, and that is a path of length 4. So the vertex list for that path would be 2, 1, 4, 6, 3. Or if I wanted to list it in terms of the edges, I could say I took the edge 2, 1, then I took the edge 1, 4, then I traveled along the edge 4, 6, and finally 6, 3, and that got me to where I wanted to go. So that's one path. could find one other path, and that would be, again, I have no choice in the beginning but to go to vertex 1, but then I could make the choice instead to go to vertex 5. So if I've instead chosen to go to vertex 5, then I can see that this is not an option, so I have to travel down this way to vertex 6, and then at vertex 6 I face the same situation as before. I could go back to vertex 1, but that wouldn't help me achieve my goal. I can't go backwards to vertex 4 because of the arrow, so I have to go to vertex 3. Then in terms of the vertices, this path would be 2, 1, 5, 6, 3. Or in terms of the edges, 2, 1, 1, 5, 5, 6, 6, 3. Now, if the edges from each vertex were sorted in ascending order by terminal vertex, for example, the edges from vertex 3 would be 3, 1, 3, 4, 3, 5. So you see they've ordered them by 1, 4, 5. If we order them this way, then recreate the breadth first search algorithm, then the path that the algorithm is going to produce is 2, 1, 4, 6, 3. So if we wanted a path from 2 to 5, then it would take that turn and we would get 2, 1, 5. But if we're just asking it to take us to 3, then it's going to produce this path, 2, 1, 4, 6, 3. And that's all right because the paths were the same length. The algorithm is going to give us a path that is the shortest, not necessarily all paths that are the shortest. So the graph that we just looked at is pretty similar to all of the graphs that we've seen so far, and that is to say it's simple enough to just find these paths by examining it. But if you have more and more vertices, it becomes less and less feasible to do it that way. So let's look at an exercise. In a simple undirected graph with no self-loops, what is the maximum number of edges you can have keeping the graph unconnected? So this kind of relates to what I was just saying. Let's find out what is the maximum number of edges we can have. So let's say suppose the graph has n vertices. Then we know we did a problem in the previous lecture note about how many ways can we connect the vertices. And we kind of drew them in, right? We said, here's a bunch of vertices randomly placed. And how many different ways can I connect them? And we decided that this was an equivalent notion to how many ways can we choose 2 dots out of however many we have. So the same thing here, except I want to make sure that 1 dot is not connected to anyone. I want to leave it out there on its own. So instead of n choose 2, as we did in that previous example, I'm going to say n minus 1 choose 2. So I have n vertices, but I'm going to leave one of them alone. And I'm just going to look at this many. And I can connect them as many ways as I want. I can keep adding edges, and that's fine. This graph will never be connected as long as one vertex is out here on its own. So n minus 1 choose 2 is going to give you the maximum number of edges that would keep the graph unconnected. And n minus 1 choose 2, we know that's equal to n minus 1 factorial over n minus 1 minus 2 factorial times 2 factorial, which is n minus 1 factorial over n minus 3 factorial times 2 factorial. So it should be n minus 1 times n minus 2 when we cancel over 2 times 1, which is 2. So you can see that as n gets bigger, if we put in a number like 100, then this is going to be quite a large number of edges. And it may no longer be so straightforward to just examine the graph and find the path. Then the question is, what is the minimum number? So the maximum number of edges to keep the graph unconnected, we said was n minus 1 times n minus 2 over 2. That means if we add one more edge, then it should be connected. So the question is, what is the minimum number? The minimum number is going to be n minus 1 times n minus 2 over 2, minimum, and then plus 1. N minus 1 times n minus 2 over 2, the same number, add 1. Okay, let's see the next question. The next question is prove by induction. This was the thing we saw much earlier in the lecture note. Prove by induction that if the relation R on vertices of a graph is defined by V relates W if there is an edge connecting V to W, then R to the power K is defined by V R to the power K W if there's a path of length K from V to W. So we're going to say, let's let our proposition, so let me pause here and say, this is proof by induction, and I told you in a previous lecture that you don't have to know proof by induction. We did some logic in this course, but proof by induction is not necessarily something you have to learn in discrete mathematics. If you're a math major, then you'll surely learn it in the future, or if you've already taken a proofs course, then you know it. But if it is something that you're interested in, feel free to read up on the technique. It's always going to follow what I'm doing here. So first, we're going to say let our proposition be the relation R to the n for n greater than or equal to 1 is defined by V R to the n. So R to the n is the relation. So this is V relates W if and only if there is a path of length n from V to W. So that's our proposition. This is what we want to prove is true for all natural numbers. So the method is we start with proving that it's true for the first natural number in our set. Often we're going to start with 0 or 1, but this could actually start at any random number, say 19, and then we're just proving that for everything thereafter it's true. In this case, it's going to start at the beginning. So we'll say P1 is true this is basically by definition. Since V relates W if and only if there's a path. So if and only if there's an edge which is a path of length 1. From V to W. So P1 is true, that's the first step. We want to show that it's true. In this case, we don't really have to show anything. Next step is assume that the proposition is true for some intermediary natural number. So in this case, we're assuming that V r to the power kW, so V relates W by the relation r to the power k, if and only if there is a path of length k from V to W Okay, then the last thing we have to do is show that since this is true by assumption for some intermediary natural number k, then it's also going to be true for the next natural number. So let's examine the proposition for pk plus 1. So this proposition would be that V relates W with respect to the relation r to the k plus 1 if and only if there's a path of length k plus 1 from V to W. So I'm going to say then for pk plus 1. So we know that this would imply that V is related by the relation r to the power k to some vertex y, and y is related to W. This is just for some vertex y. So this is what we talked about in the beginning of the lecture, composing these relations together, and we said this was exactly how we were going to define r squared. So in this case, just adding 1 to the power of r. So by hypothesis, then, because we assumed that our proposition is true for k, by hypothesis, there is a path of length k from V to Y, and there is a path of length 1, or an edge, from Y to W. That's not by hypothesis, that's just by definition. So hence, putting these two facts together, there is a path of length k plus 1 from V to W, which is exactly what we wanted to show. So usually we conclude by saying, thus, by the principle of mathematical induction, or sometimes it might be called the first principle of mathematical induction, the proposition is true for all n. We can say in the set of natural numbers if we want. If we're including 0 in the set of natural numbers, then we could say all n greater than or equal to 1. So just to kind of review the logic there, we know that the set of natural numbers, each number follows from the previous one from adding 1. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. So if we can show that something is true for the first natural number, and then we can show that some arbitrary point after that, if it's true for k, then it must be true for k plus 1, then that's essentially equivalent to proving that it's always true for a natural number. So think about that. If you are more curious about it, want to learn more, read more about it. This is just a brief introduction to mathematical induction. And what have we proved? We've proved that the relation r to the power k is defined by v relates w through this relation if and only if there's a path of length k from v to w. So that is the conclusion of this lecture, and we'll stop the video here.